All right, so we've come up with the idea of a sampling distribution. Every estimator has some sampling distribution. It depends on, well, what is the algorithm that we're applying to the data? And then it also depends on, well, what's the population of samples, right, that we could possibly get. And that determines the sampling distribution of the estimator. And now the question is, well, is that good or bad? How do we look at, if we did somehow get the sampling distribution, how could we determine if that makes the estimator useful or not useful for estimating whatever we want? So if we did know the data generating process, we could compare the sampling distribution of the estimator like we just did. We could generate a whole bunch of sample data sets and compute the estimator, and then look at that histogram, and we could compare that to the true value of the estimand and say, is this good or bad? So that's what we're doing here. And there's two very important measurements that relate the sampling distribution to the true value of the estimand that we want to think about. And the first one is bias. So bias is the difference between the expected value of the estimate. What is the average estimate that we get? If we reran our experiment a billion times and computed all the different estimates and average them, what's the difference between the average estimate that we get and the true value of the estimand? That is the bias of our estimator. This tells us whether the estimator is systematically under or overestimating the correct answer. We're never going to see this in practice, right? We're only going to see one estimate. We don't know what the true value. Bias isn't something we can measure empirically unless we have a simulation. But it's a useful quantity to understand because we'll see theoretically that certain estimators are biased in certain situations. And so you have to kind of think about, am I in this situation or am I in this other situation? So but bias is, we have to understand conceptually what it is that we're talking about. When we say that an estimator is biased, it means that the sampling distribution of that estimator is not centered on the correct value. So we're getting, if we have a biased estimator, we're getting the wrong answer on average. We want low bias, right? It may be that you can't construct an estimator that is not biased, but maybe you can construct an estimator that has less bias relative to one that has more. So an example, if we're talking about the very in this lecture, the very first example that I gave, where you're estimating like the average vaccine hesitancy. If I take the average of my 10 samples, if those 10 samples are actually a random sample from the population, I'm going to get the right answer on average. It may be highly variable, but it's going to be the right answer on average. Whereas if I go ask my friend who's an expert, they say, average vaccine hesitancy is 1.5, they may be biased, right? They may have been working with a slightly different subset of that population where it's that the hesitancy is higher or lower, or just their own personal feelings impact the guess that they get. But it's not biased it's biased in a concrete statistical sense that their guess, which is going to be 1.5, is going to be different than the true value on average. And the averaging here is simple because their guess is always the same every single time. And so the sampling distribution of their guess is just this spike at the guess, and the true value is over here. So clearly there's bias there, unless they're guessing exactly the right answer every single time. Okay, so that's bias. There's also variance. So variance actually doesn't depend on what the truth is. Variance is just a measure of how spread out the sampling distribution is. So when we say variance, we're talking about the variance of the sampling distribution of the estimate. Of course, you can take the variance of a measurement in your population, but here when we say the variance of an estimator, we're talking about the sampling distribution of that estimator. How spread out is it? Why does that matter? Well, because, again, consider that simple example. If we have a small data set, we're taking a sample average, there's a good chance that I get, even if the population average vaccine hesitancy is like 2, right? There's a very good chance with a small sample that I get a bunch of 5s. And my estimate of the population average is 5. That's really far off, right? I might be actually happier taking the biased estimate, but it's going to be at least, my average error, the difference between the estimate and the population average, is going to be smaller. Even if it's biased a little bit, it's going to be systematically off, but at least it's not going to be randomly off. So variance measures how, like, the amount on average, how randomly off your estimator is gonna be. So low variance is better. You want estimators that are giving similar answers no matter what the data are. But really, you want both, right? You want low bias and low variance. That's ideal. Another little thing that we're gonna see again and again is this idea of standard error. When we say standard error, that is the term that refers to the standard or the standard deviation of the sampling distribution of an estimator. So standard deviation is a generic term that is applied to any distribution. Any distribution can have a standard deviation, right? And it's just the square root of the variance of that distribution. But when we say the standard error, we specifically mean the standard deviation of the sampling distribution of an estimator. So it's specific to sampling distributions of estimators when we say standard error. So let's go back to the main idea here. We have, in terms of understanding the standard deviation, we have our estimand. It's what we want to know about the population. We have our estimate. It's our guess based on data. Now we have introduced the standard error, which is the true variability of our guess across the population of experiments. This standard error is a population quantity. Okay, it's a quantity. It's referring to the population of data sets, but it's a fixed number. We don't know what it is because we don't know what this sampling distribution is, but the standard error measures the spread of this sampling distribution. And that's something that we don't know. All right, so let's think about this a little bit. Let's say that I have some measurement that's distributed as an exponential. You may not have seen this distribution. Maybe you have, maybe you haven't, but it's okay. It's just some distribution. You can sample from it, like normal, uniform, whatever. And let's say that this random variable z has this distribution, and let's say I'm taking 100 samples from it, and I want to know what the population mean of z is. So I'll tell you, for the exponential distribution, the population mean is whatever this number is here. So really, it's 1. And we have two estimators corresponding to two statisticians. Statistician A says, whatever your data is, I want you to take the sample mean. And statistician B says, no, don't take the mean. I know you want to know the population mean. And so the plug-in estimator would be the sample mean, right? But don't do that. Here's a different estimator. Take the sample median of your data. That's what you should do. And they have reasons for saying that. And let's see what they are. So what's the bias and variance of the estimators in this situation? We can calculate them using R. So it depends on what this is. So we have to set up the simulation. So it's going to look like this. Again, you can break this down if you want. We have to generate the sample. What we're going to do here, the bias and variance depend on the sampling distribution, right? So the first step is that we have to generate the sampling distribution by simulation. And the second step is we're going to compute the variance of that sampling distribution, or the standard deviation of it. And we're going to compute this bias by taking the average of that sampling distribution and then subtracting off whatever true value we know to be the correct answer. Again, we can do this because it's a simulation. So let's do that. Let's start with some small number of samples just to make sure that the code works. So to generate the sampling distribution, here we know that our data are Rx1. That's what I specified here. Just in case you're like, what the hell is exponential distribution? The density looks like this, okay? It's typically has small values and then sometimes has larger and larger values. So for example, you might use this to model how long you wait for a bus or a train. If they're coming at regular intervals, you're going to show up, and most of the time there's going to be one pretty close. And sometimes you have longer waits. Okay, so that's how our thing is. Our random variable is distributed in the population of people. And my let's say I'm taking the sample mean. Let's go with the first statistician suggestion, taking the sample mean every time. And how many samples am I collecting, did it say? 100 samples. Okay. So 100 samples like this. Okay, so we'll just say sampling dist. And let's look at it. It looks like that. Okay, interesting. So you can see, just from looking at the sampling distribution, if I've told you that the true parameter, the true estimand that we're interested in, the value is 1. Okay, that's what we're trying to get. You already can see just by looking at this that this appears to be pretty unbiased. All the values are clustering around 1. But we can estimate that bias more accurately if we add more draws to the sampling distribution. Okay, and now what we can do is actually take, this is our average estimate. So actually let's rename this. Let's call this estimates. So this is our average estimate, and then we subtract off the true value of the estimand, which is 1. So this is the bias. And now we can get the variance. The variance is just the variance of this of all these numbers. Or let's do the standard deviation. So this is the standard error. So it's on the same scale, and it's pretty small, which here makes sense, right? You can just kind of look at this and say, okay, this is about 0.1 captures like 67% of this. So this should be about 0.1 here. So square root of the variance. Okay. So that's it. That's the bias and the variance for the sample mean estimator. So we have pretty low bias and reasonably low variance. Now let's do the same thing if we repeated this for the sample median. Also, all we have to do is change what the estimator is. So now we're going with statistician B's suggestion. We're getting the sample median each time. We can look at the sampling distribution. It's a little bit different. So you can see it's it changed. It moved a little bit. Let's calculate the bias. This is substantially different, right? This is not anywhere near as close to 0 as this number is. So this is like numerically 0, basically. This is definitely not 0. So this estimator is biased. And so it's kind of saying on average, if you're doing the sample median, you're going to be off by about 0.3 for this data generating process. And that's substantial. But let's look at the variance. The variance is about the same. Okay. So just make sure that ran right. Okay, yeah. So variance is about the same. So I would say this estimator is worse, right? Because you're not getting really much benefit in terms of the variance. It's about the same, but you're inducing a lot of bias by taking the sample median. So that's not good. But it depends on what the data are. So here I was doing Rx. So let's see if this changed if the original data were instead normally distributed. I don't know. Let's find out. So let's look at the mean again. So for the sample mean estimator, let's look at bias and variance. So bias very, very small, variance about 0.1. Okay. And now we can change to median. So here, for this distribution, the bias of the median is also very small. So in the other case, if the true data were exponentially distributed, the median is a pretty bad estimator because it's highly biased. But if the data are normally distributed, the median is actually pretty close in terms of bias. It still has a higher variance. So I would still say the sample mean is a better estimator in general in this case, because the variance is better and the bias is about the same. So that's how you compare bias and variance in a simulation. As you can see, it depends on what, how you're generating the data, the answer that you're going to get. And so the idea is precisely to understand what are the conditions, what is it that we need from the data, what do we have to assume about the real population distribution in order for this estimator to be good or bad in terms of bias or variance. That's precisely the kinds of questions that statisticians are interested in figuring out. Again, this is kind of abstract. You're never going to do this in practice with data, right? But it's going to help you understand what is the thing you should be doing with your data, right? If these two statisticians say, hey, you need to do logistic regression, the other guy says, no, don't do logistic regression, do linear regression. You're like, I don't know, how should I choose? You can do a simulation, right? And you can see, well, if the real data generating distribution looks like this, then this method is better. So you don't have to trust people to tell you what to do. You can often simulate and see what actually makes the difference. All right, so a slightly more complicated problem here, but really just the same, okay? So we have some data generating process that's given here. We have some value of the true estimand. So here it's the population mean of z, which is given here. Here, the thing that we want to know is this, which we can calculate from the data generating process. We have two estimators, which are this thing and that thing. What are they doing? How do they work? Who cares? We can evaluate them as total black boxes, construct their sampling distributions, and compare them. So that's what we're going to do. So first thing to do is implement this data generating distribution. That's kind of, this part here. Let's get that done. So let's say, n from 1 to 100. So first things first, x is a normal random variable, normal 0, 1. W is Bernoulli with p is 1/2. And then y okay. So this implements this over here. So that generates, okay. So that generates data sets if we want them. And then we have to compute the true value of the estimand. So we could do that in a couple of ways. One way is we can do the math, okay? So we can use the rules of expectation to compute what this is for this data generating process. But if we don't want to do the math, we can just use sampling. So we can set n really, really, really big and then compute the value of the plugin estimator, right? And that should be very close to the true value. But let's do it analytically here because I think it's easy enough. So here, this is the expected value of y. Given that, well, let's see if it is. Given that w is 1, so that's gonna be, let's see if we can. So this guy is, so when w equals 1, that's gonna be the expected value of a normal random variable with mean of x plus 1. And then this is going to be 0.1, but that doesn't matter. And then this one is going to be just x. So here I've basically just set the value of w to 0, and here set it to 1. I can tell you just by looking at it that this is going to be a 1 and that this is going to be a 0. Intuitively, why? Because x is 0 on average, right? So my mean of this normal distribution is also going to be 0 on average. And then here I'm adding 1, so it's going to be 1, and this is going to be 0. If you want to make it very mathematically concrete, you can condition here on x, so you can use total expectation. So I'll look at this one. So this expected thing is x plus 1, just put sigma again, given x equals little x, and then averaging over values of x. So here, what do we have? So this, given that x equals little x, the mean of this is little x plus 1. Done. So now we need to take the outer expectation, right? And so this by linearity of expectation is expected value of x plus expected value of 1, which is just 1. And expected value of x is 0, is 1. So this one is similar. So this difference here is going to be 1. That's the true value of the estimand. If you didn't totally follow that, don't worry too much. It's not really the kind of thing you're going to have to do a lot as an applied person. I'm just showing you so that you kind of understand. And also it's not relevant because in real life you don't have the data generating process, right? This is only useful so that you can think kind of like how would you compute this thing if you did have the true data generating process. But another way to do it is just to sample a really large sample and then compute the value of the plugin estimator, and that'll be close enough. So, okay, so let's just say true value is equal to 1. Okay, now let's do the estimators. So I've set these up as functions. So for example, if I do lm of data, oh, I didn't save this. So data equals, there we go. And now I can do lm of data, and I get an answer. I can also do plugin of data. I get a different answer. So these are both guesses. These are different guesses. Given the data, these are guesses for what this relative risk is. I know the true answer is 1. So in this case, this linear model is giving me a better answer, it seems like, than this plugin estimator. Again, you don't have to actually care what this is doing. How it's doing it, what's going on, doesn't really matter. We're just going to evaluate these estimators assuming that they're black boxes where they're just, you give the data to somebody and they give you back an answer, and I just want to know who's the better guesser on average. So let's generate the sampling distributions. So let me actually make this also a function where I say, here's how much data I want. I'll call this DGP. Okay. So now I can just give me 100 data points. Give me another 100. Give me another 100. Great. So I can do like, for this data set, estimate that. Okay. Repeat it. So this is what I'm going to do. I'm going to repeat this like a bunch of times. So let's do it 1,000 times. Estimates from this estimator. So sample size 100. The sample size is 100, and I'm getting 1,000 samples. And that's good. Okay. So let's look at what that sampling distribution looks like. Okay, there we go. So what we see, we know the right answer is 1, which is here. And these numbers are all very close to 1. So that's great. Let's do the same thing for the other estimator, the plugin estimator. And let's see here. So these are, I don't know if you noticed, but the axes changed a lot. There we go. So the LM histogram, these numbers are much more tightly concentrated around 1, and they're more loosely concentrated for this one. See, there's much more variability. You can see that concretely if we just compute the bias and variance. So let's look at the bias for the LM. So we take the sampling distribution, we find the expected value of that, and we subtract off the true the true thing. Okay, let's try this again. So very low bias. What about the variance? Also pretty small here. So let's compare these to for the same thing for the plugin. Pretty low bias, much higher variance. So this number is a lot bigger than this. Maybe it's easier to see if you look at the standard error for both of these because it's on the right scale. So this first estimator, the LM estimator, has errors on so let's say they're both unbiased, right? So all the error is coming from the random variability. So my error on average is very small here, 0.02, versus here it's about 0.2, so 10 times bigger, the error for this plugin estimator. So based on this, I would say, wow, I'm doing a lot better with this estimator, with this LM estimator. I would want to use that in practice for any real data that I think might come from a process like this one. But you can see this depends on the process. So let's skip that. Let's just work on this. Let's change the data generating process. So instead of this, let's say this x is gone from here. Okay, so now y does not depend on x, it depends only on w. And let's rerun it. Now it's even easier to show that the true risk ratio is 1 because there's no dependence on x. You don't even need to do the total expectation. But I'm just going to tell you the true risk ratio is 1 for this data generating process. I can redo the exact same thing. And now I can do the bias and the variance for that linear estimator, this LM, which I'm just going to tell you it's a linear model. We'll learn about that later. And now the same thing for the plugin. And you can see now they both have about the same variance. So the bias and the variance depends on what estimator you're using, right? In some cases, some estimators are better. But what I mean by cases is that what estimator works better depends on the true distribution of the data generally. And that affects both the bias and the variance of that estimator. So that motivates these questions, which are more conceptual. So given a particular data generating process, estimand and estimator, are the bias and variance of that estimator fixed, or are they random? And then does the variance of a fixed estimator change if I decide I'm interested in a different estimand? So for the first one, the answer is that they're fixed. So bias and variance, like I said earlier in the lecture, are fixed quantities for a given data generating process, estimand and estimator. Because if I fix the estimator, that fixes, if I fix the estimator and the data generating process, that fixes the sampling distribution. So the variance is fixed already. Once I tell you the estimand, that fixes the bias. So everything is a fixed known quantity. The only way these things vary is if I change what the data generating process is, if I change what the estimand is, or if I change what the estimator is. And now for this question, relatedly, if I decide I'm interested in a different estimand, so let's say I'm using sample mean to estimate the population mean, but then I say, actually, what if I use sample mean to estimate the population median? Does the variance change? And the answer is no, because the sampling variance of the estimator doesn't have to do anything with what the thing I'm trying to estimate is. It's not relative to the truth. It's just the sampling distribution I get. It's relative to the data generating process and the estimator, but not the estimand. So key idea here: bias and variance. Given a particular data generating process, given a particular estimand, given a particular estimator, those are fixed numbers. We don't know what they are, but they're fixed. But those things do vary for different estimators, certainly. That's how we could say an estimator is better or worse. It might have more or less variance. But they also depend, the answer to that question depends on how the data are generated, right? Like, what is the true population of interest? Maybe like we just saw in that example, maybe if I'm estimating the risk ratio for the effect of taking a particular drug on your risk of a heart attack, maybe the best estimator is a linear model. But if I'm instead working on a different problem where I'm estimating the effect of increasing the minimum wage on whether or not people get evicted from their housing, a different estimator might work better there in terms of bias and variance. So it depends on what the data generating distribution is, which is why this is why it's important to understand our assumptions about what this is, because it impacts what it is that we should be doing in terms of getting an estimator that's going to give us good estimates in general. So like I said, these bias and variance, we cannot directly observe them. We can only understand how they're related abstractly to the distributions that we might be observing in the real world. And in general, there's this kind of trade-off here, right? So oftentimes it's easy to construct an estimator that has very high bias and low variance. And that's just, okay, ignore the data, always guess the same number. That estimator has the lowest variance possible, 0, right? But it's also probably biased. And by probably, I mean, you don't know what the true effect is. If you're just guessing a particular number, it's probably not right. So there's going to be some bias there. So that's going to be a high bias, probably high bias and low variance situation. Whereas a low bias and high variance estimator might be, well, ignore anything you already know, only use the data. So if you have some kind of small sample size and you're estimating a population mean from a sample mean in that tiny sample, it's going to be very variable, the answer you get from sample to sample. But of course, on average, you're going to be getting the right answer. So there's this trade-off in like, okay, well, where do you want to be, and how can we kind of try to get in some cases, the best of both worlds? It's not always an exact trade-off. Sometimes you can, reduce the variance without increasing the bias, but it's just about understanding what we're trying to do here. And this is an important idea that will come up later. So I just wanted to plant it now.